Hi, we are Jaime and Magdalena, and today we're going to present a quick example of how to do integration with the process of trigonometrical substitution. This type of exercises consists in changing the values of a Pythagorean triangle with the values of the original function. Today the problem is: calculate the area between f of x equals to x squared times square root of 1 minus x squared, the axis, and the lines x equals to minus 0.5 and x equals to 0.5. So in order to calculate the area, first we need to integrate with the limits given by the same problem. The limits are minus 0.5 and 0.5. So as seen in the video, the s that stands for integration has on the top a 0.5 and on the bottom a minus 0.5, which represents the limits. Now the values of the complex part of the function will be substituted in the triangle so they can later become part of a series of trigonometrical identities. In this case, they will be called omega identities. So now instead of talking in terms of x, we're talking in terms of omega, as we can see in the left part of the screen. Next step is substituting the original integration with the trigonometrical integration. So first of all, we're going to write the s and change the limits because now they're in trigonometrical terms. First, x becomes sine squared of omega. Now cosine of omega stands for square root of 1 minus x squared. And the rest of the function, the dx, becomes cosine of omega times d omega, as seen in the left side of the screen. The limits were changed because of the trigonometrical rules. Now, sine squared of omega is 1 minus cosine of 2 omega over 2, and cosine squared of omega is 1 plus cosine of 2 omega over 2. So with that in mind, we can now change the equation or the integral and write again the s, the limits. We should never forget the limits, and write 1 minus cosine of 2 omega over 2 times 1 plus cosine of 2 omega over 2 times dx. As you can see, these values were changed because of the sine squared and the cosine squared. Now we multiply both values, and then again we put the s, the limits, and write cosine of 1 minus cosine squared of 2 omega over 4, because now it's multiplied, and never forget the d omega. Well, now with that in mind, we just get the 4 out of the equation because it's not needed in the integral, so we write it outside. We write our s, our limits, and now we have 1 minus cosine squared of 2 omega times d omega, which, as we all know from math 4, that's the same as 1/4 integral with the limits of 1 minus the same. We use the same method we used before. If we look at the squared on the left side of the screen, and we just substitute cosine squared with 1 plus cosine of 4 omega over 2. Now with that in mind, we change everything and we just make it in terms of halves. So now we just change it, and we have 1 minus cosine of 4 omega over 2 d omega. So it becomes, well, as you can see in the screen, du and u. We go back to the substitution method. U is for omega because it's the inner part of the complex part of the equation, and du is the differential of u, which is 4 d omega. Now we have 1/8. That 8 is because of the 2 that is inside of the last step. And now we have 1 minus cosine for omega d omega. Now we just do two different integrals. We have 1/8 d omega minus 132 as 1/32 of cosine of u du. Which makes it now real quick because we know that the integral of the omega is omega and the integral of cosine is sine. So we just write the integral and state the limits at the end. Instead of writing a c, we just put the line and state the limits because of the calculus rule. Now we have the integral is omega over 8 minus sine of 4 omega over 32, and we state the limits again. Now here's the tricky part. The limits are stated, so you can subtract the limit from the top minus the limit, or subtract the limit from the bottom from the limit from the top. I mean, if you subtract the bottom one, or the top one minus the bottom one, you get the area. So you change your omega and you substitute it with what's in the limits line. So now, as you can see here, we use the top one at first and then we subtract the bottom one. The omegas are substituted with the pi sixth and the minus pi sixth. So now that you subtract the whole thing, your area equals to 0.07677 units squared. And that's all. Now here's the graphical representation of the problem. The red line represents the graph of the original function and the blue lines represent the graph of the limits. So the area that's asked by the problem is the area that's found between those two little triangle looking shapes between the x-axis, the red line, and the blue line.
In this partial project, we learn about definite integrals and area between two intervals of the curve. When we saw graph until now, we only think about intersections, slopes, and growth and decreasing patterns. We never thought about the area. But now with these integration techniques, we can know the area. An application of real life could be that since primary school, our teachers have taught us how to get the area of shapes with the straight lines, but what happened with the curves? Now with this integration, the definite integrations, we can learn how to get area of curves and even volume.